Hi students, welcome back. Coming to the next topic, that is the minimization of the DFA. So far you have seen so many topics on this non-deterministic and deterministic finite automata, converting NFA to DFA, and to find whether the two finite automatas are equivalent or not. Now let me explain you the minimization of deterministic finite automata. So is it required to minimize the DFA? Obviously. So if you are doing some work, means try to reduce the work. So the more that reduce your work, the more you can get the free time and you can think for the another thing. In the same way, the more you can minimize the automata machines, the more it can work, the more it can capable of doing this work. So the minimization of DFA means reducing the number of states from a given finite automata. So here the minimizing means we are going to reduce the number of states that are participating in the deterministic finite automata. If suppose 7 states are there in deterministic finite automata, try to reduce the states and make it 3 or 4. If even though it reduced to 6 also, it's somewhat better when compared to the previous state. Okay, so now let's see the steps that has to follow for minimizing the DFA. So in this video, I just give the algorithm, that is the basic steps that you need to follow for minimization, and the next video I'll explain with an example. Okay, so let me try to explain the algorithm. Minimization of deterministic finite automata. The first step, what you have to do, remove all the states that are unreachable from initial state via any set of transition. What it mean? Suppose if Q1 is the initial state, okay, some Q1, it has to reach all the states. It has to reach all the states that are participating in the network. Okay, so like this. Let me take. Okay, so here 1, 2, 3, 4 different states are there. So here first is remove all the states that are unreachable. So here from Q1, 1 is reaching. Okay, if Q1 wants to reach 4, it can reach via any set of transitions. So from 1 to 4 it is going to reach. Okay, if we want to reach 2, it can reach. If it want to reach 3, it can reach. It want to reach 4, it can reach. Suppose here this direction is like this. Okay, so this is the 4 and it is coming. So here remove all the states that are unreachable. So from Q1 to I want to go to 4. So can I go? This way it is not possible. Now let's check here. From 2 to 3. Okay, 3 to 1 I can go, but 3 to 4 I can't go because 4 is coming to 3 side. So here the 4 is unreachable. So just remove that 4 from the transition. So that is the first step. Remove all the states that are unreachable from initial state. From initial state to which state is not unable to reach, just remove that transition from that node from the transition. That's first step. Second, draw the transition table for all pairs of states. So after removing this state, draw the transition table for the remaining states. The remaining states, whatever that are participating in the network, those states has to, for that you need to draw the transition table. Okay, next. Now split the transition table into 2 tables. So whatever the transition table I got, that table I want to split into T1 and T2. Why I am splitting? Okay, let me tell you. First, follow the algorithm. Then you can, after seeing the example, you can clearly understand. So, after removing the unreachable state, I draw the transition table. So, I am splitting the transition table into 2 tables, T1 and the T2. Now, T1 contains all final states and T2 contains non-final state. Means here the initial state is also there. Non-final state and initial state. So T1, suppose in a deterministic finite automata, you can get one or more final state. That we know that. So if whatever the final states that are there, that final state should be is one table, and the remaining initial and intermediate state will be in another table. T1, T2. T1 contains all final states. T2 contains non-final states. Now step 4. Okay, I divided the 2 tables, one transition table into 2 tables. Next, what I have to do? Now find similar rows from table T1. So if you take the T1, you need to find the similar rows. I had drawn the transition table, right? So in this, I need to find the similar rows. So that is the transition function. Let's say A and B is the input, and this is the transition function you get. Okay, you'll get here the transition function. If transition function, let me take Q and R. If transition function of QA is equal to the P and the transition function of Q on A is equal to P, so here also you'll get the same P and P. Okay. If you are having the similar rows, so this Q and R is having the similar rows P, 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 P. Okay. In that case, that is, find two states which have the similar values of A and B. A and B is having the same similar values, same states P, 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 and remove one of them. So here these two are equal. So just remove one state. One row you have to remove. Means I am reducing, I am minimizing my table. So remove one and replace here. Repeat step 3 until we find no similar rows available in T1. So in the same way, repeat step 3 and 4 for table T2 also, because I divide the table into two tables. One contains the final states and another contains the non-final states. So after removing the same rows, you will get a new tables. Now combine the reduced T1 and T2 tables, and finally the transition table of minimized deterministic finite automata you will get. Okay, so this is an algorithm for the minimizing. So in the next video, I'll explain with an example by taking these steps. Okay, thank you.